Okay, so it's 8:30, so I think we can start. Good morning, everybody. And so I think today we will start from the yesterday's problems. We won't be covering every problem, but if we have some time at the end of the lecture, I will come back to some problems from the previous one. So that's the plan for today. And as usual, we start with the easier ones. So I think the easiest ones from yesterday was problem D and problem F. So we will cover them like pretty quickly, I think. Okay, so the problem D prom. Okay, so basically we had two array of numbers. Numbers from A1 to AN and numbers from B1 to BM. And we want to find out the number of pairs such that the first number in pair is from one array, the second number is from the second array. So number of pairs ij, such that the difference between these numbers, ai and bj, is not greater than some constant k, which were also given in the problem statement. And n and m were like 1/4 of 10 to the 6th. Okay, so the first thing we would do with these arrays, we would sort them. So then it will be easier for us to see what's happening. And there are actually two different ways to tackle this problem. So let's assume that we have these arrays and they are sorted. So this one is sorted and the other one is also sorted. And let's say that we are interested in every pair which consists this element ai. So we are fixing I, and we are interested in every number j which is a valid pair. So we see that if ai and minus bj is not greater than k, so we know that when we have number bj, this number must be not greater than ai plus k and not less than ai minus k. So actually this gives us the range in which we would like to in which the bj must be. So essentially, in one idea is to binary search over this array B and find the position of these numbers. So we have like array B, and we do a binary search to find this number. Maybe it's in this position. Well, this number or a number which is like the first number which is not less than this one. And we can do binary search for this position. And of course, for binary search, we can use C++ lower bound or upper bound. And we do this for every possible I. So so for every possible I, we find 2 pointers with these values, and we just add the difference between these pointers to our answer. And this gives us the number of pairs which have AI on the first coordinate. So we have n log n for sorting both arrays. Well, actually, in this solution, array A doesn't have to be sorted. It's only important that we sort array B. And for every possible value in array A, and we have n such values, we do 2 binary searches for these numbers, and every binary search is log n. Yeah, so actually I am assuming that this n is like maximum from n and m. It doesn't really matter. So essentially this solution runs in time n log n. But you can do another solution. Instead of making this binary search, you can maintain 2 pointers. Because so first of all, you need to sort also array A. And suppose that we have 2 pointers which are valid for number AI. Okay, we have these 2 pointers. So when we move to the next number, a bigger number, so when we move to AI plus 1, we know that these pointers, because this number is greater, these pointers can only move to the right. So actually, we maintain these 2 pointers, and every time we are going, we move to the next bigger number, we fix these pointers to maintain this invariant. And of course, it's easy to see that every pointer goes from the beginning of the array to the end of the array. So the total time which is needed to fix both of the pointers is linear across the whole algorithm. So in the second algorithm, we have still n log n for sorting both arrays, but the second phase in which we are counting the pairs is doable in linear time. But overall complexity because of the sorting is n log n. And that's basically it for this problem. Okay, so this was a kind of warm-up problem. So let's move to the second one, to problem 10. Okay, in this problem we had a word which consisting of various characters which represented brackets. So we had 6 possible characters, opening and closing brackets of 3 kinds. So for instance, let me write the So this is the input word from one of the examples, and we know that we have such a word, and probably this word is not a correct bracket sequence. I mean that some of the brackets don't have its counterparts. So for instance, this bracket is open and it's closed, and this pair is okay, but this bracket is only open. It doesn't have like its closing counterpart. So we would like to add some new brackets, but only at the beginning of this word or at the end of this word, in such a way that the brackets in this word would be like properly nested. So every opening bracket would have its closing bracket, and the nesting of these brackets would be valid. So, for instance, okay. So what is the algorithm? So you probably know the algorithm for checking whether the bracket sequence is correct or not. So you just maintain a stack, and you put all the opening brackets on the stack, and every time you find a closing bracket, you must see whether the bracket on the top of the stack is an opening bracket of the same kind. So for instance, if you have like such sequence, you are putting this bracket on the opening bracket on the stack. So here we have stack. Another bracket is opening. You also put it in stack, and then you have closing bracket. And if you have a closing bracket, you're looking at the top of the stack and see whether this bracket is of the same kind, and then you remove it from the stack. And once again, if you have this closing bracket, you're removing this opening bracket, and so on. So you can have like two wrong situations here, or actually three. One situation is that you have a wrong bracket. So you have like this opening bracket on the stack, and you are closing it with a different bracket. Then this one is not good. Or you have just closing bracket without opening bracket, so the stack is empty, and you have a closing bracket. This also is forbidden. Or you have some opening brackets at the end of the word, and they are not like closed. So probably you have something like this, and then on the stack you have this bracket, this opening bracket, and this closing bracket. It's this guy, and this guy is left after. It doesn't have any counterpart, so this also is forbidden situation. So we have to tackle all of these situations in this word in order to try to fix them. So we also maintain a stack, and what kind of wrong situation can we have? Well, the first wrong situation is if we have a closing bracket. We have a closing bracket, and our it's not a state, it's a stack, and our stack is empty. So we would like to have some brackets, so opening bracket of the same kind on the stack. So we can do this by introducing a new bracket which was at the beginning of the word. So then on the stack we have this bracket, and when we encounter this closing bracket, we can just delete it, and we have a good pair. So then we are proceeding. We have this opening bracket, this one, and this one. Then we have a closing bracket. So we are eating this guy. And we are left with some open brackets on the stack. So we need to close them. So in order to close them, we just put the closing ones at the end of the word. So basically, these are brackets which we have to, we are forced to put at the beginning or at the end. And basically, if And we are, thanks to these brackets, we are fixing two possible wrong situations. The situation when we have an empty stack at some point, and the situation when we have some opening brackets left at the end. But there's also a situation in which we have a bracket of the wrong kind. So, for instance, if we had something like this, so we had this guy on the stack, and this guy would be of the different kind, would like to close it, then we cannot fix this situation. And if we encounter something like this, we have to say that answer is no. Okay, so that's pretty much it. Yeah, so the question was, we would like to fix the sequence. We'd like to fix the sequence using the smallest number of brackets, but we see that these are brackets that are necessary to put. So basically, we cannot do with the smaller number. So basically, in this problem, the solution is it's quite easy to see that this is like the only possible solution. Okay, and as usual with this stack algorithms, the time complexity is linear in the size of the word. Okay, so that would be it. Okay, I see that there are more people than at the beginning, so actually I have some two questions for you. Well, one information and one question. The information is that I opened some of the CDs, but I got some questions. I opened the contest for absolving for both of days. Yesterday, I actually opened it right away after the contest. I tried to do today and for the next contest also. Just after the contest, I opened it up for absolving, so you can do this. And I got some questions about time limits. So for this contest, we usually in Poland we don't present time limits for the tasks. But since you were asking about this, I can do this if you want, informing you about the time limits for the next contest. What is the time limits? Do you want this information? Okay. Okay, so they won't be included in the task statements. There will be some public announcement in the system with the time limits for every problems. Okay. All right. So. Okay. So now we can move to the problem B. Okay, in the problem B, we had some we had a question about whether a certain set of inequalities has a solution or not. So inequalities were of the general form of inequality was. We have two variables. So in general, we have variables from x1 to xn. And we have our inequalities are of the form that we take two variables and we take them with pluses or minuses. So actually, we have like 4 possibilities here. And we said that this sum must be greater than 0. And we are just asked whether this set of inequalities has a solution or not. So one of the ideas to solve this is actually to we can look at the a little bit simpler set of equations. Mainly, let's say that the only possible types of equations are inequalities are xi minus xj is greater than 0. So basically, this is the same as saying that xi is greater than xj. So we can make a graph in which every variable is a vertex in this graph, and we have edges in this variables which goes from, let's say, from the smaller one to the bigger one. So we have some x1, x2, xn. These are vertices. And for instance, if we have like inequality that xn is greater than x2, so we can just write an edge from x2 to xn. Okay, and what we have to test in this graph is whether this graph has a cycle or not. So why is it the case? So it's easy to see that if a graph has a cycle, then we don't have any solution. Why is that? Well, because if you have a cycle, so that means that you can go from some vertex, let's say x2, using some other vertices, and you can go back to vertex x2. Well, this means that you have like this chain of inequalities that xn is greater than x2, and xj is greater than xn, and so on. And finally, you got back to x2. So basically, that boils down to x2 is greater than x2, and that's clearly not going to. Clearly, we cannot put any variable which will satisfy this inequality. So so basically, we are testing if the graph has a cycle. So if the graph has a cycle, the answer is no. We cannot satisfy these inequalities. Okay, so what happens if the graph does not have a cycle? Then we have directed acyclic graph, namely DAG, and we know that we can make a topological sort on this. So basically, we can find like the ordering of the vertices in such a way that every edge goes into one direction. So in this picture, it goes from left to right. So we can find this ordering of the vertices, and so basically we can assign any variables to this any numbers to these variables, as long as the number which is assigned to the vertex which is to the right of some other vertex is bigger. So we're just assigning bigger numbers. So we can just assign like 1, 2, 3, and so on up to n. And then every inequality which is like which is denoted by the edge is satisfied. So otherwise, we say yes. And of course, because we can, we just saying the no or yes. We don't like in the answer. When the answer is yes, we don't need to show a valid solution. So we actually don't have to make a topological sort on this graph. This is only important for the proof of that this really works. But of course, if we were asked to show some possible solution, then we would make this sorting of the graph. Okay, so that's how we solve the easy part of the question. So when we have only this kind of inequalities. So here actually we have two more inequalities, because we have also xi plus xj is greater than 0 and minus xi minus xj is greater than 0. The fourth type, when we are taking minus xj plus minus xi plus xj, it's essentially the same as this. So we have these two additional types. And it may be not quite obvious what to do with them, but it turns out that after like tinkering a little bit, it turns out that it's useful to actually introduce additional vertices to our graph. So here in this graph we have only vertices which represented like the variables, and now we will build a graph which represents variables and their negations. So we will have vertices like x1 up to xn, and we will have another vertices which represent minus x1 up to minus xn. Okay, and we will do the same. We will do the same transformation as here. So we will make the edges in this graph. So basically, if we have this this general case, so plus minus xi plus minus xj is equal to is greater than 0, then we can move one of these variables to the other side, and this is, we will basically make two edges for this inequality. So we will have an edge from plus minus xy is greater than, and here we change the sign. So this will be like first edge, and the second edge would be if we put xi on the other side, so that will be plus minus xj is greater than minus plus xi. So of course we need to, depending on which signs are here, we are making both edges, but we are, for the first edge we are changing the sign of xj, for the second edge we're changing the sign for xi. And yeah, and we are just building the same kind of graph. And the algorithm is basically the same. If this new graph has a cycle, then the answer is no, and if it doesn't have a cycle, then the answer is yes. And why is that? So basically, to see that if a graph has a cycle, the answer is no, the argument is pretty much the same. So if we have a cycle, we know that we can go from some variable, we can go through other vertices and go back to the same variable. It doesn't really matter whether it's like this kind of variable or this kind of variable, but we know that there is some variable, and after going through the cycle, we end up with this kind of inequality. So it cannot be satisfied. So if this graph has a cycle, then the answer is no. A little bit more tricky is to see why the answer is yes if we do not have a cycle. The problem is that okay, we still can do some kind of topological sort, but the problem with this is that these vertices here are not like totally independent. Because if we, here we could give the value for every variable like kind of independently. But now, if we give the variable, for instance, for x1, we know that the variable, like we know the value which should go to the minus x1. Yes? If we put 5 here, we know that in minus x1 we also need to put minus 5. Okay, but the idea is as follows. So we know that this graph doesn't have a cycle, so actually we can make some kind of topological sort of this, and one of property of such a graph, which is a DAG, is that there's some vertex. Well, here, for instance, this is this vertex, or perhaps this vertex, which doesn't have any outgoing edges. So the outgoing degree of this vertex is equal to 0. So we just find such a vertex. So let's say that the out degree of vertex, let's say xi, is equal to 0. So we don't have any outgoing edges from this vertex. So we don't have any vertex which must have the greater value, bigger value than xi. So actually, for xi, we could just put like the maximal, some kind of maximal possible value. But we must be careful what happens to the vertex minus xi. But the happy thing about this construction of the graph is that this graph is pretty much symmetric in terms of pluses and minuses. So basically, that means that if outer degree of this vertex xi is equal to 0, then in degree of the vertex is minus xi is equal also to 0. So there are no like vertices before minus xi. So actually, the value for minus xi also can be like the most negative value in the graph. So actually, we can put like the big value here and the big negative value here, and there will be the same, and we can just remove these vertices from the graph, because they will be like they will be satisfying all the inequalities which are like if we have xi here, it doesn't have any outgoing edges, it has some edges which go into this, and we have minus xi, it doesn't have any incoming edges, but it has like edges which goes here. But if we put like the big value m here and the very small value minus m here, then all of these edges here will be satisfied, because we are just assuming that that this guy will be greater than any other value that we will put here. So basically, we are removing this vertex, and we assign value for the rest of the graph recursively, because we know that since the big graph doesn't have a cycle, the smaller graph also does not have any cycle. So pretty much the algorithm is the same. Still, this is only for proof that this construction works. We doesn't really have to construct this assignment. Okay, So what is the time complexity of the solution? So we had n variables, and we had m inequalities. And we are constructing here a graph with 2n vertices and 2m edges. So basically the size of the graph is n plus m, and since finding whether the graph is acyclic or not runs in linear time, the algorithm will run in linear time. And that's it for the problem. Okay, any questions? Okay, so now we will move to the problem L, the problem about the postman. Okay, so in this problem we had some tree. The tree represents a city. Each edge is a street, and each vertex represents some kind of building. And we had a postman which has to deliver letters to every building, and so essentially we need to find some kind of path through these vertices, and this path like visits every vertex at least once. And what we would like to minimize is the total time in which every vertex will get the letter delivered. So, and like going through every edge takes us time equal to like 1 unit of time. So for instance here, in the first vertex, we say that the letter will be delivered in time 0. If we go here, it takes us 1 unit of time to go through this edge. So in this vertex, the letter will be delivered in time 1. For this guy, the letter will be delivered in time 2. And now we need to go through 2 edges to go here. Then here we will have time 4. Then we will go 5, 6, 7, 8, 9, 10, 11, 12. And the answer is like we would like to minimize the sum of all of these numbers. And we can take any path we want, and also we can start in any vertex we want. So we don't have to start in this vertex. We can choose any starting vertex, and we would like to choose it in such a way that it minimizes this sum of all of these numbers, and we have to return the minimal sum of the numbers. Okay, so usually in this kind of tasks, when we are asked about some optimal thing in the tree, it's useful to actually have this tree rooted. in some vertex, and then maybe do some dynamic programming or some like greedy observations. So still we need to find a vertex in which we would like to root the tree, because we are free to choose any vertex. So let's say for simplicity that we know that that we know the optimal vertex for the root. So basically we can root the tree in this vertex, for instance this one, and the tree will look like this. We have this our root, and we have some subtrees. Okay, so we know that we are starting from the root, and we are going like we have to go through to one of the subtrees, and then we can make like some kind of path through this subtree. Then we can go to the other subtree and so on. And we would like to find like what is the cost of the optimal path. So here we have like I would say a little bit too much freedom. For instance, we can ask ourselves, for instance, one question: can we? Is it like optimal, or can we have to visit some subtree several times? So like maybe some optimal path will go to some vertices in the second tree, and it will go to the third tree, and then it will go back to the vertices from the second tree. So so the question is whether should we consider this kind of paths, and it turns out that it's quite intuitive that this should be like quite costly. So like this shouldn't be a case. This could be shown a little bit like this. If we go to if in some optimal path we go to this second tree for the second time, so we still have to like visit all these vertices here. So it's actually better to just remove this part and go to this tree in the second time, because by the removal of this part, all of these vertices will be covered faster, and actually this can be shown that this will give us a better solution. Unfortunately, I don't know like the pretty easy proof of this intuition, but we will get to the formal proof later. So let's suppose that this is pretty much good intuition, so we can like assume it and then proceed with our solution. And later we will see that this is really a valid intuition. So now we are assuming that every tree, if we go to a subtree, then we have to visit all of the vertices in this subtree before going to another subtree. Okay, so now is the question: in which order should we visit our subtrees? So now I think there's no like clear intuition what to do. So maybe we can do some like some calculations. So let's say that we have a root, we have our subtrees, and each subtree has its size. So Si is the number of vertices in the subtree, in the ith subtree. Okay, and we know that we can like recursively calculate the optimal path inside the subtree. So we can know that we have like kind of optimal path here. And let's say that if we start in this vertex, let's say that when we start in this vertex, we have time 0. So we can calculate the sum of the times which will need to visit all of the vertices in this subtree. So this will be Ti. So the Ti is the sum of times of visiting vertices in the subtree, assuming, so let's say that this is the vertex U1, U2, and so on, assuming time in UI is 0. Okay, and we have this for all the subtrees. Okay, so basically, based on that, we can calculate the value t for the whole tree. So what we are doing here. So let's say that we are visiting these subtrees in this order. So as this subtree first, then this subtree, and so on. So what we get here? So the total time of visiting them is, first we have to visit all the vertices in this in the first subtree. So if we fix time 0 when visiting these guys UI, the total time to visit all of these guys is T1. Yes. So so what is the total time to visiting these guys if we start going from the root? Okay, so if we start from this vertex, we know that the total time of visiting all of the vertices in this subtree is T1. So what is the total time of visiting them if we start in this vertex? Yes. So for each vertex here, we have additional one time of unit. And we have S1 of these vertices. So the total time for them will be T1 plus S1. Okay. So, and then we go back here to the root, and then we want to visit the vertices from the second tree. So once again, like if we have time 0 here, we would have T2, but we are not in time 0 here. We are some later. So we need to add for every vertex here. So we have S2 of such vertices. We need to add the time in which we are in this vertex. So what will be the time? Time is 2 times S1 because we know that our path will be like based on this assumption that we are like visiting every subtree before entering another subtree. We know that here in this tree we have S1 minus 1 edges, and we have another edge here. So in total here we have S1 edges, and we have to traverse each edge 2 times, like going down and going up. So actually we need to traverse this number of edges in order to get to the root, or is it like +1? Okay. Yeah, it's it looks like it's a +1 because we still need to cover this edge. Okay, and so what about the another guy? So another guy is T3 plus S3 plus what? Okay, so it's 2 times plus 2 times S1. So these are these edges plus 2 times S2, because this also covers this edge, plus 1. And this is this edge. Okay, so we see here that basically if we have like addition vertices, so let's say that we have like k of them. So the kth one would be tk plus sk, and here we'll have 2s1 plus 2s2 plus 2s k minus 1 plus 1. So essentially this boils down to, let me continue here. So t equals to, first of all we have the sum of all the t's. So we have sum from all the ti, and plus for this plus ones here. So we can say that here we also have like 0 plus 1. So from all of these plus ones, we have just sum of si. And we also have 2 times sum of products of si times sj, where I is greater than j. Okay, we have something like this. Okay, so what can we observe from this sum? Yes. So basically what we have here, that the order of the subtrees really doesn't matter. This sum is pretty much symmetric in terms of the reordering of the trees, because here we have just sums. So if we reorder the trees, they don't change. And here we also have every possible ordered pair of ij. So this also doesn't change when we change the order of the tree. So basically what does it show us? That every like ordering of the tree gives us the same answer. So so basically we can say that every path which every DFS path through this tree will give us the same answer. So every DFS path will give us the same answer. And actually, every DFS path will give us the same optimal answer. And so how to prove this without this, like, pretty much, I would say, a little bit complicated calculations. So let's say that we have some ordering in which we are visiting the vertices. So we have, let's say that we have some order, and let's say what is the. So let's say we have some order, and let's say what is the minimal time to visit ith vertex in this order. Okay, so as we know before that if this vertex is ith on the list, so we had to visit I-1 preceding vertices. So we know that we need at least around 2 times I minus 1 edges to visit all of these vertices. So we would need 2 times I minus 1 edges if we want to visit I minus 1 vertices and go back to the root. So this is like the minimal time if we want to go back to the root. But if we want to stay in the ith vertex, we can like subtract from this the depth of the ith vertex. Okay, so this is like the minimal time we need to spend to go to this vertex in any ordering. And we can see that if we go by DFS ordering, actually this will be achieved. That DFS ordering will get us for every ith vertex, we will need this kind of time. So pretty much this proves our theorem that DFS path will give the same answer, which is optimal. Okay, so what is the time complexity to calculate this number? Yeah, this is linear, but we had one assumption. We assumed that, okay, so what we have assumed? Yes, that we know what is the root. So basically this fact tells us that every DFS path will give the same answer as long as we are starting from the same root. And it turns out that different roots can give us different answers. So what we have to do actually is to calculate this answer for every possible root and then take the best one. So if we do this in the naive way, we would get like so this is one root. So for every possible root, it will give us an n squared solution. Okay, so we can do better, and there are several ways to calculate the answer for every possible root. There are like a pretty much hard way and an easy way. So I think a hard way here would be to use the general dynamic programming. For instance, you can really calculate all of these values, ti for every subtree, and then try to also calculate these values for the remaining part of the subtree. And then using like the 2 passes of the dynamic programming, you can calculate value t for every possible vertex. But this is quite complicated. There's actually a little bit easier way to do this. And let me write it here. So basically what we can do, we can calculate the t for one of the vertex. So let's say we calculate the value t here for this vertex. And then we would like to calculate this value t after moving to some child. So let's say that now we are moving from this vertex to so let's say that this is vertex v, and we have calculated tv, and this is some vertex u, and we will like to calculate what is the difference between tv and tu. If we know this difference, we can go from tv to the vertex, and then we can go through other vertices. Every time we go through the edge, we would adjust the value using this difference, and then we can like make the traversal of the whole tree, maintaining this value, because we know how to adjust this value using when we are going through one edge. So if this difference is known, so if we're going here, we will add difference, and when we go back through this edge, we would subtract this difference, and every time when we are in the vertex, we know the value for this. Okay, so we know that. The optimal answer for vertex V is TV, and actually we know that every DFS traversal through this tree with root V will obtain this value TV. So actually also the traversal in which we first go to the subtree of U. So we can say that we have this path. We first go here, then we traverse this tree, and then we go back, and then we traverse the rest of the tree. So there exists this path which gives us the TV. Okay, so now we would like to know what is TU. And once again, there is a path, the DFS path which starts in vertex U, which first go to this subtree, and then it goes to the other part of the tree. Okay, so what will change to the times for these vertices? So let's say that here in this tree we have S vertices. So basically in the rest of the tree, excluding the root, we have n minus s minus 1 vertices. So this is the number of vertices here. Okay, so when we because in path from V we need to traverse this edge in order to get to this subtree. This will give us +1 for every vertex in this tree. So when we are starting in vertex U, this actually gives us -s, because for every vertex here we are starting one unit of time earlier, because we do not have to traverse this edge. Okay. So this is for these vertices in this subtree. Okay, so let's see what happens for these guys, vertices in the rest of the tree apart from the root. So when we start from vertex V, we have to go one edge to U, then we have to visit this tree, and we have to go back through this edge. So this is like 2 plus the length of this path here. But when we start from U, we have to go with this path and then only one edge back. So actually, for all of these vertices, we also have one edge less. So we have minus n minus s minus 1. Okay, and there is one vertex which is left, and this is the root of the tree. So in traversal from D, the time of visiting this vertex was 0. And now the time of visiting this vertex is non-zero, because we need to, we're starting from U, we go through the whole subtree here, and then we need to go back with this edge. So how much do we have to pay for this? We have here a subtree of S vertices. So how many edges do we have to traverse? We have 2 times s. This would cover the path from, because here we have s minus 1 edges, and this is like the s edge. So this would cover a little bit more, because this would cover 2 times this edge. And we only have to go 1 time this edge, so this is 2s minus 1. Okay? So we need to sum these values. So it will give us minus n plus s plus 1 minus s plus 2s minus 1. So this will cancel out. This also, and this is 2s minus n. So basically, so basically tu minus tv. So this is the difference between them is 2s minus n. So we can, when we are going through one vertex to the subtree of size s, we have to add to the current value 2s minus n. When we are going back, we have to subtract this value. So we can go through the whole tree, and this will allow us to calculate the optimal times for every possible vertex. So we can do all of this in linear time, because first we need to do a DFS to calculate this value, and then we need to do another DFS to propagate this value accordingly to all of the vertices. Okay, so that's it for this question. Okay, so maybe now for something a little bit different, let's try to tackle one of the harder problems. So a problem which was solved by, so already it is solved by one team, or even 2 teams. And the problem K about blocks. Okay, so this was a combinatorial problem. We were asked to calculate the number of n permutations. Which has A elements visible from the left and B elements visible from the right. Okay, so that means if we treat the elements of the permutations as some kind of stacks of certain heights. So, for instance, if we have like permutation 1, 3, 2, 5, 4, so we can draw this kind of stacks. Okay. So we can say that the stack is visible from the certain direction if there's no bigger stack which is before. So, for instance, if we are looking from the left, we are certainly this stack of size 1 is visible. The stack of size 3 is also visible, but the stack of size 2 is not visible because this is the stack of size 3 is greater, and this is like covering the stack of size 2. And the stack of size 5 is also visible. So from the left, in this permutation from the left, we have 3 visible stacks. So so here A is equal to 3. And what happens from the right? So from the right we can 4 is visible and 5 is visible, and like 5 covers everything else. So from the right we have 2 visible stacks. So this is an example of a permutation of 5 elements. So here n equals to 5, in which we have 3 elements visible from the left and 2 elements visible from the right. So namely, we need to calculate the numbers of such permutations, and the limits in the task were n was up to 50,000. So n was up to 50,000. A and B was up to 100, and actually we had multiple queries of some NAB. So basically, we will be aiming for a solution which, after some kind of preprocessing, will give us the ability to answer each such query in constant time. Okay, so as usual, I think it's pretty much good to, if we don't see an answer to the problem in full generality, we can see if we see answer to a little bit easier problem. So let's say that we ignore one of the directions. So let's say that we ignore the directions from the right. We are only interested in the directions from the left. So so in this case, this permutation would be a permutation of 5 elements, which has 3 elements visible from the left. And let's say that D and A is the number of such permutations. So number of n permutations which has A elements visible from the left. And actually, this kind of numbers are known in combinatorics as the Stirling numbers. So there is, maybe you know a recursive relation which like relates these kind of numbers to the smaller ones. It's kind of similar to the equation from the binomial coefficients. And And if you don't know this, this also can be like we can figure it out because the proof of this is not very complicated. So the idea is, okay, we have some. Let's say that we have a permutation. So we are just like writing this as this heights. We have some permutation which has n elements and I elements visible from the left. So we can ask a question: where in this permutation is the smallest element? Like where is 1 in this permutation? So so one answer would be, okay, so 1 could be visible. So if 1 is visible, where it should be located? In the first position. There's no other way. So we can one possible type of permutation is that 1 is visible, so this is located in the first position. And if we look at the rest of the permutation, we can like treat it like like an n-1 permutation. We can just like decrease the height of every other element by 1, and this will gives us a 1-to-1 correspondence with the permutation of n-1 elements. And so this is okay, so let's see, n-1 elements. And how many elements are visible in this smaller permutation? A-1. Because this 1 was visible, and now we have this less visible elements. So basically, we have this 1-to-1 correspondence. Then we can say that the number of these permutations is actually a number of these permutations, and this is the case where 1 is visible. Okay, so the other case is when 1 is not visible. So actually, when 1 is not visible, it could be located in every other position because it will be covered by every possible stack here. So once again, when we remove this 1, we would get an n-1 element permutation. And how many visible elements will be there? A. Because in the second case, so we can write it once more. So 1 is somewhere here, and if we remove this 1, we would get n-1 element permutation, and we have A visible elements because all of the elements which were visible before, they are visible in this smaller permutation. So once again, we can say that this is the n-1 A, and we have to multiply it by the number of places where 1 could be put in this smaller permutation. And this smaller permutation has n-1 elements, and 1 can be put after each of them. It cannot be put in front of, because there we would get this case. So we have n-1 positions of 1. So this is the case when 1 is not visible. Okay. So basically, like I said, this recurrence relation is pretty much is very similar to the recurrence relation from to binomial coefficients, because you don't have this this can we like know that such recurrence is satisfied? Well, either you can know this because these are Stirling numbers. They're like in you can like read about it in concrete mathematics, for example. You can try to find a proof which looks something like this, or you can actually guess it using the computer. So usually when you are dealing with like calculating the number of permutation which satisfies some properties, usually it's good to like write a brute force solution which shows you how little numbers, like how the numbers of permutations for little values of n and a behave, and either you can like just look at these numbers and maybe figure out what is the recurrence relation between them, or you can say, okay, I know that many recurrence relations look like this, so that they the recurrence from n and a, it somehow depends on the smaller values, so the values in the preceding row and maybe smaller values here, and maybe these values are multiplied with some coefficients. So you can actually write a solution which tries different coefficients and see which satisfies the values you calculated from the brute force solution. And maybe this will give you a recurrence, some kind of recurrence relation. Maybe you can then later prove it, or you can just assume that it's true. It's not like the 100 bulletproof solution for this thing, but if you don't if you don't have any other ideas, you can at least try it. Maybe it will work for your problem. Okay, there was a question. It's 1 to n. Well, actually, if an element set if every item is different, then pretty much it's the same as a permutation. It doesn't really matter. If in this, if it will be some kind of multiset when the elements could like appear multiple times, then probably it's not valid. Then you will have to. Then probably this recurrence would be trickier to get. But if all elements are different, then it's pretty much the same. Okay, so this would give us the answer to the easier problem, because what we'll do here, we can just calculate this recurrent, like we can calculate just the whole table, because n times a would give us like 5 million elements. So we can like calculate everything, and then we would just answering queries in constant time. Okay, but this is the easier version of the problem. So what happens with the general version when we also have elements? When we also have to consider elements which are visible from the right side. Okay, so one idea would be to. Okay, so let's try to write down a similar equation to this one. So let's say that we are interested in what is the number of D NAB. Okay, and it turns out that the same idea applies here. Now we need to consider 3 cases. Once again, one case is when the smallest element, so the element I, is visible from the left. So if it's visible from the left, we can treat the rest of the guys as the n-1 element permutation. It has a-1 elements visible from the left because we removed 1, and still has b elements visible from the right. So it will be d n-1, a-1, b, and this is the case when 1 is visible from the left. So symmetrically, you have the case when 1 is visible from the right. So you would have d n-1, a, b-1, because now you have, like, when 1 is visible from the right, you have 1 less element visible from the right in the smaller permutation. So this is the case 1 is visible from the right. And we are left with the first case where 1 is not visible, and then you can see that we have a permutation with 1 element less, and because 1 is not visible from the left and not visible from the right, we have A and B visible elements left. And you have to multiply it by the number of possible positions for 1. So now you have n-2 possible positions because you cannot position 1 on the left and you cannot position 1 on the right. So this will be multiplied by n-2. So this is the case 1 is not visible. And I saw that at least one of the teams came up with this solution and coded it, and unfortunately get time limit exceeded. Because if we want to calculate the whole thing, it would give us the time complexity of n times a times b, well, plus complexity of answering the queries, but this is, if we have this table, this is like constant time for each query. But n times a times b with this with these constraints is too big. So we need to do something more clever here. Okay. And actually, it's not a coincidence that I started from this simpler problem when we have only one we are only considering visibility from one side, because it turns out that the problem with visibility from two sides can be this can be reduced to the problem of visibility from one side. And I think that this reduces pretty tricky. So basically, you need to see how can you transform a permutation in which we are interested about the visibility from both sides into a permutation in which we are only interested in visibility from one side. And it turns out that if we have a permutation, we can like we can mark all the visible elements. So let's say that these are visible elements, and each of these elements, except for the biggest one, it covers some elements which are after it. So, for instance, this guy, if we are looking from the left, it covers some guys here which are smaller. And again, this guy covers some guys here which are smaller, and this guy covers here. And if we are looking from the right, we have the same picture, and here we say that this guy in the middle, the highest guy, does not cover any element. Okay, so one interesting property here which we are gonna use is observe that all of these guys, because this is a permutation, they have different heights. So actually, what we can do, we can move all of these on one side of this big element. So basically, what we do here, we will take these guys. Okay, we will take these guys. We will reorder them, and we will put them here. So this will be in such a way that this guy, which is visible from the right, it will be visible from the left, and it will cover all the other elements. And we will do the same with these guys here, and we will put them here. So a picture would look like this. First, we would have the smallest guy which covers some elements. Then we will have this one. Then we would have this one. And then we will have this guy, and the highest one. And the highest one. Okay, so from this permutation we can get this one. Okay, and basically we can try to reverse this procedure. This procedure is like a reversible if we know which elements which are now every element is visible from the left, and if we know which elements we would like to move to the right, this is pretty much reversible, because we can like take this guy and all of the elements which are after him, because we know that this part ends with the next visible element from the left. But we need to consider here different possibilities of choosing which elements go to the right. So here we have n. Let's say that here we have n permutation, and we have A elements visible from the left and B elements visible from the right. Okay, so this corresponds to this permutation. And how many elements we have here? So this will be n permutation, and we have A plus B elements visible from the left. So the question is, can every such permutation can be transformed back to some permutations in which we have elements from the left and elements from the right? Okay, here I hear the answer yes, but actually the answer is not really. Because here in this picture we have one little assumption which is important when we want to do the back transformation. So here we have the assumption that the last element doesn't cover anything. Yes? Because if we had some elements here which are not visible from the left because the last element covers them, then we cannot, then like in this procedure we don't know what to do with them. So actually this this cannot be like reversed. So what we do here, we will assume, we need to assume that this element is, the highest element is fixed. So like the highest element is the last element in the permutation. So this will actually gives us a little less freedom, but we can say, okay, so let's just ignore this element. We know that this element is here, so we can just try every possibility for other elements, and other elements will give us n-1 permutation. So if we ignore this guy, here we will have n-1 permutation, and how many elements are visible from the, well, actually here we didn't have a plus b left elements, we had a plus b minus 1, because here this guy is counted twice, and here we have this counted once. And if we ignore this guy, we would be left with a plus b minus 2 elements visible from the left. Because here, ignoring this guy, we have a minus 1, here we have b minus 1, so in total we have a plus b minus 2 left. Okay, and the last thing is, so we know that every n-1 permutation in which we have a plus b minus 2 left elements can be transformed to this kind of permutation, but we need to calculate how many possibilities we have to put the elements on the, to put a elements on the left and b elements on the right. So actually a minus a elements, which are here to the left, and b minus 1 elements to the right. So how many possibilities do we have? Yes. So yeah. So when we go from the this n-1 permutation to here, we must choose from a plus b minus 2 elements, which are all on the left. We have to choose b minus 1 element, which will be put to the right. So basically that means that the value d n a b, so the number of these permutations, is equal to the number of these permutations, d n minus 1 a plus b minus 2. So like I'm reusing the d for 2 arrays, but I think this this makes no confusion, and it must be multiplied by this binomial coefficient. So we are multiplying it by a plus b minus 2b minus 1. Okay. Okay, so what does it mean for the time complexity of the whole solution? So essentially, if we want to answer the query NAB, we first need to know the value d for such numbers. So actually, we need to calculate this. I use the. I have used small d. So we need to use we need to calculate this, this smaller table. And we know that we can afford this, because this is like 50,000 times 200. So we can calculate this array. And we also need to calculate binomial coefficients, but these are like up to 200, so this is also pretty much easy to calculate using the standard recurrence relation in quadratic time. So we will be calculating this like in time n times a plus b plus a plus b squared to calculate both these tables. And if we have these tables, we can answer the query in constant time. We just multiply two numbers. So we can get also plus q for the queries. Okay, and that's it for this problem. And I think we can make a little break now. Okay. Okay, we'll be starting the second part. Okay, so now we will tackle the problem of problem A, album of numbers. Okay, so in this problem we had to implement a data structure which allows us to insert numbers, to remove numbers. So the standard operations we encountered before. So we can say insert x, remove x, and after each operation of insertion or removal, we were asked to calculate the the average number of the smallest element in every possible non-empty subset of the numbers in this structure. So let's say that we need to calculate some kind of average. And the numbers in this structure can be repeated. So basically it's a kind of multiset. And maybe let's write down an example, because it's pretty much gives us what is happening here. So basically, if in our structure we have elements 1, 2, 2, and 5, we can have different subsets here. So for instance, we can have like let's say we can have a subset 5, only 5. We can have like 2 and 5. We can put also 2 2s here. We can put 1 2. We can put, and we have also like the counterparts with 1. So we can have 1 5. We can have 1 2 5. We can have 1 2, and we can have 1 2 2. And we also have the element which is 1. So basically these are all possible multi-subsets of this multiset. And for each of these subsets we are interested in the smallest value. So the smallest number of each subset. So here we have 5, 2, 2, 2, 2, and in each of them we have 1. And we'd like to calculate the average of all of these numbers. And we would like to calculate this average after every insertion and every removal of the element. Okay, so what kind of observation we can do here? Actually, it's easier to look at this problem when we considering all possible subset. So I will introduce also the empty subset here. And let's say that like when we're calculating the average, this will count as 0. We will look later how to get rid of this this empty subset. But now we are considering that it's here, and like the minimum element in this subset is 0. Okay, so one observation is here that if you look at this, how these subsets are constructed, you can, for instance, see that if we consider element 1, which is the smallest one here, for every subset which does not have 1, so these are all of these 6 guys here doesn't contain 1, you have a corresponding subset which does contain 1. So these are here. So like the subsets on the right were constructed from the subsets on the left by just inserting 1. And also you can go with this further. For instance, how can you create subsets which contains 2? So let's say that we forget about 1, and here if you have every subset which contains 2, you can from this construct subset which contains additional 5. And basically here you will have subsets which if the number of elements is taken more, you can take more than once, then you will have to consider all of the cases. And okay, so what does it mean? So it means that we can, when calculating this average, we can group this the subsets which have the same minimal value as ones. Okay, so actually this is not what I meant here. Actually, I meant what is happening with the elements which have 2 as the minimal guy. So if you have, if you want to construct the elements which has 2 as the minimal guy, you can take these elements without 2. So this is this guy and this guy. So the empty set and 5, and to each of them you can add 1, 2, or 2 elements 2. So basically, if you know that you have like a certain number of subsets which does not have 1 and does not have 2, so you can introduce 2 times more subsets which contains 2 as the smallest element. Because for everyone you can put 1 2 or you can put 2 2s. So basically in our solution, when we are adding and removing numbers, we will be maintaining for each we will be maintaining the set of numbers, and for each number we will maintain also the number of occurrences. So like you can say some kind of multiplier for the number. So let's say that we have numbers x1, x2 up to let's say xk. So these are values which are in our multiset, and we have like multipliers for them. So we have k1 elements. Okay, let's k1 elements of value x1. We have k2 elements of value x2, and we have ks elements of value xs. Okay, and let's say that these elements are actually that they are ordered. So the x1 is the smallest element, and so on. So we can ask, we have several subsets possible, including the empty set, and we can ask in how many of these subsets the element x1, which is the minimal element in through whole elements, is the smallest guy. So maybe let's say that k1 is equal to 1. So we have only one smallest element, and this is the case in our example. So as we said before, we can partition every we can partition subsets into two parts. One part is all the subsets which does not have 1. So they are not interesting now because we are calculating the subset which has 1 as the smallest element, and the subsets which contains 1, so they have 1 as the smallest element. And we can see that there's like one-to-one correspondence between them, because like there's correspondence between these two subsets, because for this guy you can add 1, for this guy you can remove 1, and you can this one-to-one correspondence. So basically, if there's only one element 1, you have half of your subsets which will have 1 as the smallest element, and half of the subsets we will have some different element as the smallest one. Okay? So if k1 is equal to 1, then we would have something like this. If we want to calculate our average, then on average, 1/2 of all these subsets will have x1 as the minimal element, and 1/2 of all these subsets which will have some other element as the minimum. And here we have a smaller problem, because here we know that these subsets we don't have 1 at all. So we can go here recursively. So let's say that we go recursively, and let's say that k2 is equal to 2. So this is the same as in our example. So we have 2 values of 2. So let's look at this picture. So once again, we have some correspondence between the subsets which do have 2 as the smallest element and the remaining subsets. So we have 4 of these guys which has 2 as the smallest element and 2 remaining subsets. So it looks like our multiplier is not 1/2 but 2/3. Yes, 2/3 of this, because 4 out of 6 subsets which are remained has 2 as the smallest element. And actually that makes sense, because for each of the subset which does not have 2, we can make 2 additional subsets which has 2, because we can put 1 2 or we can put 2 2s. So basically then we would have 2/3 of x2 plus 1/3 of something else, and so on. And we will so basically we can so this is like for other case when k1 is equal to 1, k2 is equal to 2, but we can make a general case. So for the general case, we can see that if k1 is equal to like anything, then we know that for each subset which does not contain x1, we can add 1 x1 or 2 x1s or up to k1 x1s. So basically, k1 divided by k1 plus 1 subsets will have x1 as the smallest element. And the remaining subsets will have something else as the smallest element. So we will have this, this multiplier. And then we do things recursively. So here we have k2 divided by k2 plus 1 x2 plus 1 k2 plus 1, and so on. And we finally will get to the case when we have ks times ks plus 1 times xs, and here we will have to consider empty subset. So this will be the only the last subset which will be considered, because like in this case we considered 1, we considered 2, and then we will consider 5. So there's like one-to-one correspondence between elements subset which has 5 and subset we do not have any element, and this will be empty subset which is here. So we can say that okay. For now, we just put here 0. We assume that this is an additional subset which has element equal to 0. Okay, so this will give us an average. So if the task would be okay, so we have a fixed structure. So we have a fixed like a multiset and calculate the average. This would be a formula which allows us to calculate this in linear time, depending on number of elements, different elements. So this will give us O of S time. Okay, so there are two cases to consider now. First of all, okay, so maybe let's first of all fix this formula, because in the task we don't want to calculate the average with the empty subset. So we would like to get rid of it. So actually, this empty subset is quite useful if you want to calculate this formula, but we would like to get rid of this part. But this is pretty easy here, because we must see what kind of coefficient will this 0 get. So actually, formally, we can write here, this is 0 multiplied by 1 times k as plus 1, and if you multiply all the values which are before this 0, you will get that this 0 is actually multiplied by 1k 1 plus 1 times 1k 2 plus 1 times 1k s plus 1. Okay, so we are calculating the average of x1, x2 up to x3 with some how to say, some weights. We calculate weighted average, but we also add element 0 to this weighted average. So basically, let's say that this weight here is equal to k, or let's okay. So let's maybe say that this is equal to 1 over big K. So big K is just multiplication of all of these values. So it turns out that we have to multiply this average we get with some number which is corresponding to k to get the average without 0. So by what we should multiply it? Okay, so the idea is that our average looks like this. This is 1 times over k multiplied by 0 plus 1 minus 1 times over k multiplied by something else. And this is like the real multiply by the real answer we would like to have, because we are like adding okay, is this correct? Because like we are we would like to get the average of the numbers from x1 to xs without the 0, and we would like to get it from the average in which we include 0. And this in this average in which we include 0, we like multiply 0 by this coefficient. So like everything else is multiplied by this coefficient. So it turns out that if we want to get the answer from the average, we need to multiply the average by the by the inverse of this, this coefficient. So the answer would be just average divided by 1 minus 1 over y minus 1 over k. I think I okay. Okay, so that's how you get rid of this empty subset. But still, this will result with pretty much slow solution when we want to recalculate this average from scratch every time we insert or remove elements from the structure. So how to tackle this? So we can do this in two different ways. One way is to use some kind of range tree or segment tree over the set of these numbers. So basically, what we do, first of all, we will read all the input to get all the possible numbers which will be ever inserted to the tree, and we will build a binary tree over the set of these numbers. And in the tree, in the leaves of the tree, we will just store the current values of k's. So for every leaf, we will in the insert we will just add 1 to the certain k, or with the removal we will add -1, and we will build the tree, and in every leaf of the tree we will have a partial information about some kind of segment of this formula. And actually, in that it will be useful to store two pieces of information in the leaf: the partial value and the partial multiplier. And they are like it can be done. The calculations are not very involved, but they can be a little bit tricky to do this. But this can be done this way. And in this solution, we would get n log n solution, because n is the number of all the operations. So we'd get at most n different numbers in the tree, and update of the tree during the insertion and removal will give us logarithmic time. But this was the hard way to do this. Actually, there's a easier way in which we do not have any tree at all. And the easier way, for the easier way, we have to look at the precision of the answer we are asked. So in the answer which we are going to calculate, it's not like the answer with infinite precision, because you cannot like store this and in the computer. So the doubles or long doubles have certain precision. So the author of the question also asks us to give the answer up to 10⁻⁶ precision. So let's see how these numbers are going like to incorporate to the average. Well, one observation is that if these numbers are like sorted, and we have at least one number of each kind when we are doing this calculation. So these numbers here, these coefficients, are actually smaller or equal than 1/2, each of them. So this guy, because K1 is at least 1, so this guy is smaller than half. This guy is also smaller than half, and this guy is also smaller than half, and so on. So every time we go into another bracket here, we will multiply the multiplier by another 1/2. So these numbers we will get pretty fast, very low. Okay. So every time we multiply, we divide these numbers at least by 2. So it turns out, what is like the, so after some iterations, these numbers will get so little that actually the remaining part of the formula will be so negligible, it will give us no additional information. Like it will be pretty much close to 0. So we can just, after some steps of computation, we can just throw it out, and we can calculate how many do we need, because the numbers which get here, so the values x can get as big as 10 to the 9th when divided by the precision we need. So 10 to the -6, we will get that we will need at least 10 to the 15, and so we need to calculate how many times we need to divide by this number to get to 0. So we need to calculate the logarithm of 2 of this number, and from my notes, it looks like it's around 50. So we can say that after like considering 50 smallest integers, 50 smaller values of x, we can just throw away the rest of the calculations. So basically that means that we can just make a map with which maps the values x to the corresponding multiplies, and every time we do insert or removals, we just update the map, and we calculate the whole formula from scratch, but only taking into consideration 50 or so smallest elements. And this will give us the time complexity of like n log n for updating the map, plus n times this number, like 50, to calculate the formula from scratch. And this will also pass. One thing which can be quite tricky in this task sometimes when you get some formula wrong with doubles, you can get, especially in this problem, you can get like very little or very big numbers. So it's easy to make some mistake which results in returning like infinities or very small numbers. And sometimes it can get you into runtime errors when you get some infinities, when you get some or wrong answers when you get infinities, and sometimes even it can get you time limit exceeded probably when you get some little numbers which have some weird representation in doubles and which can be really slow. So you have to be a little bit careful here. So probably like with the approach with a tree, it can be quite tricky. With this approach, if we are like cutting after fixed number of elements, it should be okay. Okay, so this is all for this problem. I personally like this kind of problems when you have like two almost totally different approaches to the task, because I think I saw both of the approaches in your solutions, also with tree and also with cutting after several elements. Okay, so this was album of numbers. Let's maybe speed up a little bit so we can get to at least two harder tasks. So we will make today we'll make also insects and board game, and maybe some problems we'll move to another day. And okay, so let's start with insects. Okay, so in this problem we had to prepare some specific for killing insects, and so each kind of insect needs 3 times of some mixtures to be neutralized. So we have n times of insects. We have mixtures of the first kind, of the second kind, and of the third kind, and every insect is determined by the triple A, B, C, so AI, BI, CI, and this means that if we want to get rid of the insect of this type, we need to in our mixture, we need to put a mixture of the first type, which is called AI, of the second type BI, and of the third type CI. And we need to pay for every mixture here. So for every AI we pay, let's say we pay A, for every BI we pay B, and for every CI we pay C, if we want to buy them. And if we have, so if we bought AI, BI, and CI for the same insect, then we get P. We get a reward P for for the mixtures which neutralize this kind of insect. And we would like to maximize our profit. So so that means that we have some different AIs. So let's say that we have like A1, A2, A3, and so on. We have B1, B2, B3, and C1, C2, and C3. And we can buy them, and like buying each of these guys, we pay for this capital A. For these guys, we pay capital B, and for these guys, we pay capital C. And we have n insects. So let's say that we have like insect 1, insect 2, up to insect n. And if you want to get a reward for the specific insect, so for instance for insect 2, we need to we need a certain values. We need to buy one of these guys, and one of these guys, which are described by this tuple. So unfortunately, this is not very good because I mixed some notation. So basically, that means that this guy can choose, the second insect can choose any of these guys. So for instance, he can choose A1, he can choose B2, and he can choose, like, for instance, C1. So like the tuple for this guy is A1, B2, and C1. So I have some coincidence with the names of these guys. So let's say that these are like alpha, beta, and gamma. Okay, alpha, beta, and gamma, and each alpha belongs to the set A, I to A. Let's say it was, I think, 256 in the problem, and betas are from B1 to here, and gammas are from C1 to C. Okay, that will resolve the conflict with notation. And for every type of index in the insect, we have this triple. So for instance, for insect 1, we could need to buy A2. We can need to buy the same B2 here as for the second guy. And if it's needed for 2 insects, we only pay once here. And we can pay. We can ask here for C3, and so on. And for n, we also have some correspondence here. So basically, what is happening here? So we need to select some of the vertices on the left side, and when we select for every vertex selected, we need to pay some amount. So if we select this guy, we pay A. If we select this guy, we pay B. And if there's the case that we selected 3 vertices, which corresponds to the triple from the specific insect, we get paid for this insect. So we get a reward for getting rid of the insect. So for instance, if we select this one, this one, this one, this one, and okay, if we select something like this, we pay A plus B plus C. So this is okay. So let's say that we put minuses here because we are paying this, and let's see what kind of insects we get rid of with these values. Okay, so for the insect 1, we are still missing a C3, so we don't get reward for insect 1. For insect 2, we have A1, we have B2, we have C1, so we get plus P for insect 2, and for insect 3 we don't have B3, C3, so we don't get anything from the insect. So basically, in this solution we will get a reward of P minus 2 times A minus B minus C. So of course it's easy to see that this is, in this case, this is not necessarily an optimal solution. We would like to maximize this, of course, because here we're paying for A2, and without paying for A2 we get the same, like we get this reward P, but we spent less. But maybe the more optimal solution would be to actually buy also C3, so to pay C more, but then we get another P for getting rid of the first insect. So we need to do some kind of optimization here. So usually when we are seeing this kind of optimization, we have some elements of one kind, some elements of the second kind, and we need to somehow make some optimization between them. It's usually a good idea to look maybe some kind of maximum flow or some kind of matching algorithm will be useful here. And actually, this is right approach in this task, but it maybe it's not so easy to see where how this actually corresponds to some matching to some flow in some grid. One thing which can be misleading in this task is that we have like three groups of different ingredients or mixtures, and actually this does not really matter here, that we have exactly three groups, and actually we can like treat all of them as the same. It could be like one group, or it doesn't really matter that we pay the same amount for all of these guys. So this could be quite misleading. The second thing is we have different signs for treating these elements, and we have different signs for treating these elements. So I mean, for these elements we have to pay something, and for these guys we are paid. So usually in the when we are trying to do some flows, when we are we actually try to incorporate these values into some capacities of the edges, and usually the capacities are on the same sign. So either if you go through the edge with some capacity, you get for instance you get paid, or you have to pay something. So it will be more useful if we have the same sign on both of the sides of this graph. And actually we can do this by saying something like this. Okay, I would like to make this one as a payment. So we would like to make that we also need to pay for the insects. And this can be done as follows. Let's say that we say, okay, we can get rid of what if we can get rid of all of the insects? Then we are paid n times p. Like this is the maximal amount we can get if we can get rid all of the insects. And then let's see which insects we are not killing, and let's pay for these insects. So actually here we will need to pay for insect 1 because we are not killing them, and for insect n. So this is the same as saying we have n times p minus 2 times p minus the cost of this. So now, like, the costs of both sides are the same. And actually, for I draw this in such a way that it kind of looks like the how the net will look like. So here we will have our source, and here we will have our target vertex, and we will have edge for every mixture to the source and for every insect to the target vertex. And the capacities of these edges will be the same as the amounts we have to pay. So actually, these capacities will be we will make them positive. So let's say that these edges, all of these edges for A, we have capacity A. All of these edges from B will have capacity C and B, and all of the edges here will capacity C. And the same will be for the edges to the target vertex. All of these edges will have capacity P. Okay, so what we have here, we would like to maximize this value. So the only positive value here is n times p. The rest of these guys are negative. So we would like to minimize this value. If we have a graph like the flow, usually we have like algorithm for maximizing the flow, and it is the same as minimizing the minimal cut through the graph. So it looks like we'll have to minimize some cut through the graph, and when we are making a cut, we are paying for the edges we are cutting. So we are paying for the capacities of the edges we are cutting. So actually, if we will, so basically this boils down to this: if we have some cut through this graph, and if we are cutting like this kind of edges, this will mean we have to pay for the certain ingredients. When we are cutting these edges, we will have to pay for the insect. Okay, so how to do this in a way that it makes sense? So actually, when we have some cut, the cut goes through every possible path through the net. So if we have some path from the source vertex to the target vertex, so for instance we can have a path through A3, a path here, and through this guy. Okay, so we are cutting. So we are cutting this path. Okay, so this means what happens if we want to, if we would like to have the like the sensible payment out of this graph. This means that either we have to pay for every possible ingredient for a certain insect, or we have to pay for the insect because we don't have any ingredients. So if we consider one path which goes through the ingredient and then it goes to the insect, either we have to cut it through the insect, so we have to pay for the insect, or we have to buy this ingredient because this ingredient will be needed to this insect. So either we need to cut through this edge, or we need to cut through this edge. So we can say, okay, so for for all of these edges which are in between, we make the capacities of this edge infinite. So this will mean that it won't be like in the minimal cut. It won't be possible to the minimal cut. Won't cut these edges at all, because it's like the if you want to get a minimal value, it will be like if we cut at least this edge, we get the answer infinite, and we can see that we can just like cut all of these edges here, and we will get some smaller answer. So the minimal cut won't cut these edges at all. So for every path, it will cut either the edge from the insect or the edge from the ingredient which is needed for this insect. And this is basically what we are looking here. So every such cut which does not cut these edges will correspond to some possible payment for some possible correct payment for the ingredients and the insects. So basically, and the other round, if we have a possible payment, it corresponds to some cut in this graph. So basically, what we need to do here is find a minimal cut in this graph, and it will correspond to this value, which must be subtracted from n times p. Okay, so basically that's it. One question would be, what is the time complexity of this algorithm? Well, it is the time complexity depends on what kind of flow algorithm we will use. The one discouraging thing would be that the number of insects and the number which corresponds to the number of vertex here is up to 1,000, and we have like 5,000 edges or so. So we could think that the flow algorithm would time out, but it turns out that it's not. It will be hard to prepare a case which really like maximizes the theoretical worst case of the flow algorithm. Usually, the flow algorithms are especially in such a graph which has like very simple structure, they're usually faster than like the theoretical worst case. So here you can use like almost any like sensible flow algorithm. I think that the team which uses Dinitz who solved this problem, and it passed like in 0 seconds for the one. So it was even you didn't have to use such fast flow. Okay, so that's basically it. Okay, and we have, unfortunately, we have only 10 minutes, but I think we can give some clues about one more problem. Okay, problem G Boardgame. Okay, so in this problem, this was a geometry problem. We have n colored points on the plane. So we have points of different colors, and okay, and we wanted to find a pair of points which has different colors and which are as far as possible from each other. So we would like to maximize the distance between 2 points of different colors. So yeah, so for instance, this pair looks promising, but maybe this pair is even better, and we need to return this length. Okay, so this looks like one of the standard problems in geometry, mainly to find a pair of 2 points which are farthest from each other. So basically, if we ignore any coloring here, and if we just have to find 2 points which are farthest apart. So let's recall how to solve this this standard problem. So one thing to notice is if we have some points, then the furthest pair must be located on the convex hull of these points. So basically, what can we do is to make a convex hull, and then we pretty much sure that the farthest pair is on the convex hull, because if it was like somewhere in the middle, we know that we can extend this line to touch the convex hull, and if we go through this line, like for the one of the other vertices, we will get even longer line. So the pair of points is located on the convex hull. Okay, but still, you can have a test like when even all the points are located on the convex hull, and still you need to find this pair fast. But we can use the idea which was presented in the previous geometry problem. I mean, we can do some radial sweeping over this convex hull. So the main idea is that if we look at the pair which is furthest, this pair must be a pair of antipodal points. So if we think of some line which touches this convex hull, and if we think about the parallel line which touches the opposite side of this convex hull, so we see that like the distance between those lines, like the further part of the points must be of this kind. So basically, if we find the further part of points, then if we put 2 parallel lines here, they will like enclose this convex hull. So basically, what we can do, we can start like make two lines here and start rotating them. And after rotating them, you will get the current distance between antipodal pair of points. So basically, maybe after, if we turn it out, it turns out that it will go something like this, and this will be the second candidate for the furthest part of points, and we do the full revolution around this convex hull. So once again, it's there are only finite number of interesting positions for these lines, because we need to consider only, like if we go a little bit further, we need to only consider this edge and this edge to be the next angle. So this, if we have this convex hull which is sorted, we can do this full revolution in linear time. Of course, as it goes with geometric problems, this can be a little bit tricky to implement to cover all the corner cases, but this is like pretty pretty standard standard algorithm. So you can like find the implementation and like it in many books about the computal geometry. Okay, so but this is like the standard thing. So what will happen if we have colors? So once again, it's good to see what will happen if we have a simplified problem. And by simplified problem, I mean we have only two colors. So for instance, we have some red points. So these are actually blue. So we have blue points and we have some red points. Okay. So by the similar arguments, we can show that we only need to consider blue points which are on the convex hull of all the blue points, and the red points which are on the convex hull of all the red points. So basically, we can, first of all, we can calculate the convex hull of these guys. And we, again, by the similar arguments, we can make this parallel lines, but now we need to make one parallel line which touches the blue convex hull, and the second parallel line which touches the red convex hull. And when we are rotating these lines, we have to like maintain this invariant that they are like they are parallel, and this one line always touches the blue convex hull, and the second line always touches the red convex hull. And once again, this can be done in linear time in terms of number of vertices of both convex hulls. Okay, so this is case where number of colors, so number of colors is equal to 2. Okay, so what happens if of course we need to so like the rotating part is linear, but of course we need to calculate the convex hull first. So this will give us the n log n algorithm, because we need to find the convex hulls. So for two colors we have n log n. Okay, so now what happens if we have like the any number of colors? So once again, here we can I know at least two algorithms for doing this. One is a little bit more harder. You can do some kind of divide and conquer on the number of colors. So basically, what we are doing, you're dividing the colors into two bags, and then you are telling something like this: either like the furthest point is in one bag, so and then you are just doing it recursively, or the furthest point is in the second bag and you are doing it recursively, or the point is between one point from the one bag and the second point from the second bag. And then you can say, okay, so I recolor every point in the first bag to one color and every point in the second bag to the second color, and now I have two colors, so I can use this algorithm. And it can be done, but it's a little bit tricky to implement. And actually, there's a simpler solution to this. So let's suppose that that we numbered these colors. So let's say that we have color number 0, color number 1, and color number 2, and we have like up to possible even n colors. So if we take two colors, which are basically represented by two numbers, so these numbers will be different on at least one bit. Yes, if you have like two numbers, binary numbers, if they're different at least on one bit. And because the numbers are from 0 up to n minus 1, there are at most logarithm number of bits in these numbers. So we can say something like this. Okay, so let's look at ith bit, and let's partition the colors into two bags. In the first bag, you will put all the colors which have 0 on this bit, and in the second bag, you will put all the colors which have 1 in this bit. So basically, you are recoloring all the colors into two colors. So then, if you have this recoloring, you can apply this algorithm for two colors. So basically, you are seeing one bit. So recolor to two colors, differentiating on ith bit, and use this algorithm which runs in times n log n. Okay, and you are like running this algorithm for every possible bit. So you will get the total running time n times logarithm squared. Yeah, and because every two colors must differ in one of the bits, in at least one of the pass of the algorithm, they will get into two bags. So if you have like the longest some optimal pair, it will in some bag. So in some one of the logarithm n invocations of the algorithm, they will be in different bags. So you will find this optimal pair. So this will give you n log squared n algorithm. Okay, but it can be speeded up a little bit. We can speed it up to n log n. Okay, why is that? Let's look at what we really need to do inside this algorithm. So we have logarithm number of phases, but what is the time complexity of one phase? We said that this is n log n because we need to calculate the convex hull of each bag, and then we need to make this revolution. But the thing is that the revolution we can do in linear time. So actually, we can do it faster. So what about calculating the convex hull? Can we do it faster than n log n? If you have two convex hulls, you can merge them. But how can? Yeah. But how can you get these two convex hull to merge? I mean, you need to calculate another convex hull of the full bag. Yes. So this is actually the good idea. So so the n log n part from the convex hull comes from the fact that we need to sort the points. If we have points sorted in some way, so for instance for Graham scan in the radial way, or there's some other convex hull algorithms which runs like when the points are sorted in the normal way, then the construction of the convex hull is actually linear. So what we can do, we can make this, we can sort the points at the very beginning of the algorithm. So we need n log n sort to sort them, and then during each logarithm n phases, we can make the whole process in linear time. Like because we have points sorted, so we can find every convex school in the linear time. So the total runtime of the algorithm will be n log n. And that's pretty much it for this algorithm. And I think that it's pretty much it for today. Thank you.